Okay, hello everyone. Thank you for being here on this very last talk of HCC this year. So I'm Stefano, I'm researcher at Nethermind. I'm presenting today a topic that I really like to talk about even these days after recent announcements from Google. It is about how we can rethink PeerDAS on Ethereum using a new scheme, a polynomial commitment scheme that is post-quantum secure. Okay, so I will start with a very high-level intro of why we need DA on Ethereum. So with the scalability roadmap of Ethereum, we introduced this concept of rollups, and these rollups are using data that was posted on blobs. Why on blobs? Because we introduced this new transaction type to don't overload Ethereum blocks. And yeah, so blobs are not stored in the main blocks, right? So they are stored as a sidecar and distributed over the network. And in the very first implementation, we had blobs distributed entirely to all the validators that were checking the blobs. And to introduce a kind of commitment to this data that were distributed around the network, we used KZG commitments. These commitments gives us some very nice properties of binding with the data. So it was interesting on the next level how to verify this data. And we will see this in a minute. The problem with KZG is that it is not post-quantum secure. So what's next? Quick agenda for this meeting. First of all, I will give an overview of what we have today with PeerDAS and what's the problem with post-quantum security with KZG, and introduce a new scheme, a new polynomial commitment scheme that is used. It's called FRI, and this is a suitable polynomial commitment scheme for post-quantum security. It introduces some overheads and some complexity, so we present here a solution to mitigate this complexity. We conclude with observations and the trust assumptions of our approach and the next steps. Okay, so with PeerDAS, we introduced this cool concept of data availability sampling. With data availability sampling, we allow validators not to download the full blobs, but just some chunks of the blobs. And very high level how it works, we take the blobs, we put the blobs in a matrix from the proposer side, the proposer encode the blobs with an erasure code, extending the blob for some repetition, and then distribute columns of this erasure coded data to validators. We recall that we have in the blocks the commitment we can commit using KZG to these blobs, and we include the commitments in the block. So the block remains light, and we can distribute it over the network. While from the validator perspective, we just download some chunks of this data and receive also as a tiny proof, which is constant size, that we can use to verify the validity of the chunk. And this is called the KZG proof. So both the KZG commitment and KZG proof are constant size, which is quite cool, right? Because we receive this proof, and what we can do, we can verify that the encoding was done correctly. So we achieve these properties of encoding validity. Sorry. Right, so, and this is a cool property that comes with KZG. Another property that PeerDAS gives us is data availability, right? So if we have many validators that sample, then eventually we expect that from the majority of validators, we can reconstruct the original data. So the data is indeed available. Right, so what's the problem with post-quantum security? The problem is that KZG is based on traditional cryptography building blocks. Is based on pairings operations and elliptic curves like BLS signatures are using. So with quantum adversaries, this is not very nice. Here in this slide I have an example. So we have our super powerful quantum adversary, which is our proposer with a red hat. And this guy, what can do the same thing of erasure coding the data from the blobs, but now he can forge a commitment that from validator point of view, it's a valid commitment. But what it can do, it can now send chunks of data that are not really valid for that commitment, even though they look like valid. So in this case, the validator will verify the chunk and verify against the commitment, and it will be happy. So it looks good. But the problem is that encoding validity is broken. So behind this commitment, the data you are receiving is not binding to any real data. And data availability even is broken because if the validators try to reconstruct, they will reconstruct nothing or garbage. Good news, we have some alternatives to KZG. We can use something called hash-based polynomial commitment schemes that under the hood use hash functions, which are resistant to quantum adversaries, and they're plausibly post-quantum secure. But there are some problems. So let's first see a valid candidate for this. And the valid candidate is FRI. Is an interactive oracle proofs of proximity for codes. And in very high level, I won't spend too much here, but it's a protocol between a prover and a verifier, where the prover, you can think about it as a block proposer, and the prover can claim to know a valid piece of data that has been erasure coded. So here you see as an array of elements. And this data is valid from the point of view of the commitment. So the commitment here is not a KZG commitment anymore, but you can think about like Merkle tree like commitment. So you use Merkle trees, you commit to the data, and you share the commitment with a verifier. And here the initial commitment is just a few hashes, right? The root of the Merkle tree. Now, the protocol is interactive in the sense that the verifier wants to get convinced that the commitment is valid, and to do that, he will just ask positions of the initial data. So he will ask for position number 1, position number 10, and with this interaction, the prover will answer with the value of the position along with a proof, where since we are talking about Merkle trees, the proof is an opening of the Merkle trees. We iterate this again and again until the verifier gets convinced from a probabilistic point of view that the commitment is valid. And now we end up with this proximity proof. You see it on the right, which is an object that includes commitment plus a bunch of openings, right? And this gives us a very good value for encoding validity. But how about data availability? Let's try to put FRI in a real practice, in a real use case. So this image is similar to what you saw before. We have a validator that is trying to sample, but now in a block we are not adding KZG commitment, but we have this proximity proof. And as you can see, it's very large. The proximity proof is distributed over a block to everyone, and validators will receive it. When the validator sample a column, he will receive the sample object plus its own opening, plus the commitment with the proximity proof. That's a lot of data, isn't it? So from the network point of view, it's a huge overhead. And these larger commitments are a bottleneck nowadays for this solution. Just trying apple-to-apple comparison. We implemented FRI, and we compared it with KZG, and you can see here, the example is for 21 blobs, which is the state-of-the-art of Fusaka with maximum number of blobs available, and with FRI with 128 queries in the proximity proof. This is just for security, we can parameterize this. But in this case, you see that we have a huge difference in terms of sizes, in dimension of 100 of kilobytes. So, what's the approach, the intuition behind I'm presenting today? So the approach is the following. By observing FRIs, we realize that FRI has this interesting structure of that can be distributed in terms of the verification point of view. And this is because the protocol is interactive. We can make it non-interactive, but let's say that the protocol is interactive, in which the verifier will ask one position and receives back the value and the proof. So the intuition here is that we could split the proof for the proximity into small chunks, and we can ask a committee of trusted parties to verify those individual proofs. Now, what the result here is that every party in the committee will just verify a smaller proof, is just a couple of openings, in this example it's just one, and provide an attestation. If the majority of, if the whole committee provide the attestation, then we have a certificate, right? And here again, we are talking about post-quantum stuff, so we want this attestation to be post-quantum secure. We can use a post-quantum signature, which is around 3 kilobytes per signature, but we can aggregate them in a ZKVM. Okay, so the committee gives us, the certificate gives us the same security of a proximity test, and now we need data availability. So in practice, again, what we could do is that instead of putting the proximity proof within the block, we just put the commitment, which is a few hashes, and the certificate. And we distribute it to the network. So now from a validator perspective, when I want to sample cells and columns, sorry, what I have to do is just receive a single object, which is the object I'm sampling, plus the opening, because we are talking about Merkle trees, plus the commitment with the certificate. So the verification is much lighter because I just verify a signature for the committee validity and then my received opening. So in this approach, we sample only for data availability. We don't sample for encoding validity. The encoding validity is offloaded to the committee. We implemented it, and this is just a rough example. So in our distributed verifiable approach, this diagram is for a committee of 100 validators in the committee that are providing a post-quantum signature that we can aggregate with a ZKVM. And you see the advantage. In our case, the commitment is around 100 kilobytes. Of course, the sampling proof is the same, but is a big advantage in terms of network overhead. And of course, we buy post-quantum security. There is no free lunch. The problem here is that we are drifting from universal verification from a different trust model, right? Here we trust a committee of parties that have to perform the heavy lifting for us, and we trust them. So encoding validity is on the committee, and the data availability is still on the global validator set. Of course, we could do better. We could, for example, consider some threshold in the committee. So let's say we have 2/3 of honesty in the committee, but this would require us to increase the number of queries in the proximity test because you want some repetition to cover the 2/3. We do have a preliminary implementation of the scheme. So if you guys want to have fun, you can go to our repo. You can benchmark both FRI and our distributed version of it. There are many parameters that you can use. You can change the validator side, the committee side, and all the parameters that the FRI protocol requires, and observe different values in the results. Next steps. This is the most exciting part. As I said, there are so many parameters that can be configured, not only on the committee side, but also on the FRI side, because the protocol has many different parameters, repetition parameters for the encoding and all the stuff. So very interesting is to benchmark everything and try the sweet spot between the size of the committee and also the post-quantum signatures, because they introduce some additional overhead that we have to balance when we talk about aggregating them and compared with the distribution of the FRI protocol. So in one side, we increase the committee. On the other side, and reduce the complexity of FRI, but we increase the complexity of the signature of the certificate. So the sweet spot has to be found. If the committee is corrupted, we could do something like fraud proofs, where the validation will check that the committee was corrupted and try to challenge it. And also another interesting part is that this protocol could be completely compatible with ePBS, where we have this delayed verification, and we introduced already the concept of committees in the protocol, in the Ethereum protocol. This should be a thank you slide with my, yeah. Thank you, guys.
Yeah, hi, thank you for the presentation, and thanks for benchmarks this, and I was wondering for the benchmark also for a while. And I'm wondering, like if we are using, like, it's kind of like a delegated, like, DA, right? So if you already ask, like, 100 committee members to verify the encoding, right? So why do we still need a FRI here? We can just simply like encode the data hash, Merkle hash it, and then just let this 100 or which it doesn't matter what's the size of your committee, right? Just download all the data and decode it, right?
You mean to download? You don't want them to download the whole data, right? Because potentially you want to increase the number of blobs in the data. So you don't want to send the data over. And
no. I mean, if like the DA is why we want the DA to be like minimum consumption on the bandwidth consumption is because we want like everyone joining the network want to be the validators. They can download the data, so we need to control this part. But if you only have like just 100 or I don't know how much like a committee member need to check the encoding, right? Then they don't need a FRI. They can simply download the data, and it's just 100 times the like blob size. It's not any overhead for the network at all.
Yeah, again, it depends on the size of the blobs we're talking about. Right?
I mean, let's talking about even 100 gigabyte. And then you times with like one gigabyte. You times 100 is 100 gigabytes. How large it is?
Yeah, but you still want to allow the sampling part, right?
Yeah, but your sampling part only checks the data part, right? You only check the data integrity, actually. So which basically...
With the commitment.
Yes, so which means you didn't check the encoding, right, by individual members. So which means any hash tree is already enough, right? I just open. It doesn't change that part, right? It's what I want to say is like, if in this situation, you don't really, in your setting, you don't really need a FRI here. You can simply download all the data. It does the same exactly like outcome with FRI, but without FRI, and you can get actually higher confidence.
Yeah, probably can be a good approach, but I still believe that if you want to change the protocol then and increase the committee or change parameters in the committee, you still want the flexibility of the proximity test.
Okay, yeah, thanks.
Thank you. No more questions.